Welcome back to Code Deconstructed. In the last episode, we took a look at an email address parser from Pandoc. And I mentioned that it's difficult to load a large project like Pandoc into GHCi. But it turns out there is a way using cabal-dev, which uses the cabal file information in a project to load what's necessary into GHCi. So you can see that a number of Pandoc modules are loaded and we have a prompt. So let's try parsing an email address like we did in the last episode. And some functions that we need aren't in scope. So let's import those now. There's Parsec and Pandoc's parsing file. Let's try again. And there we go. So we didn't need to create a separate file this time. We're evaluating code from within the Pandoc source code. Now let's try parsing some Markdown. We'll need the name of a Markdown parser from the Pandoc source code. So let's take a look at the source, and there's a readers directory which has a markdown.hs file. Now, before diving into a file of this size, I like to take a look at it from a high level, scanning through the function signatures. And we can do that with Emacs occur, which will show us all lines matching a regular expression. And a function signature is any line that starts with one or more word characters, a space, and 2 colons. So right away you can see that there are a number of parsers in this file. Looks like there's upwards of 100. And I'm looking for one that looks familiar, namely a header parser. And there's one called header, so let's give that a try. So let's parse a header. Code Deconstructed. And it's telling us that header is not in scope. So let's import it. Pandoc, readers, Markdown, and try again. It's still telling us that header is not in scope. So why is that? Well, if you look at the file, you'll see in the module declaration that only one function is exported from this file. And GHCi doesn't allow us to use any of the hidden or private functions from it. So how do we go about testing the functions inside this file? Well, it turns out that GHCi will allow us to do that, but only for interpreted modules. So if we load with an asterisk first the module that we want to work with, it should give us access to the functions inside of it. And it does, but we ran into another error that parse is looking for a parser state, which we haven't had to deal with before. So you can see that the header parser, in the type signature, there's parser state. And to save some time, there's a default parser state that we can use. But what's going to be even easier is using this read markdown function that accepts a parser state and a string to parse and returns a Pandoc value. Let's give it a try. Read markdown, default parser state, code deconstructed header. And we get back a Pandoc value, which is some metadata on the document, and then a list which has a header inside it and some more information inside that. It's essentially a parse tree that shows us Pandoc's internal representation of a parsed markup document. And it's what allows Pandoc to convert to and from as many formats as it does, because it uses this intermediate representation. Also, Pandoc allows you to convert a file to this representation directly without opening up a GHCi session. Pandoc has a type called native that if we convert a document to that, you can see a similar output to what we saw before, but with no metadata on it. And we can convert arbitrarily large documents to native format from Pandoc, such as the README we were working with previously. So you can see a number of different elements in here. It's a little bit hard to read with all the nesting, but fortunately there's an Emacs extension called Rainbow Delimiters that should make it a little bit easier to see what's going on. So there's a header, a paragraph with some embedded emphasis, another header, another paragraph, a link, and so on. Now I like to be able to use the rainbow delimiters inside of GHCi as well. So rather than running cabal-dev from the command line, we can run it from inside of Emacs. Now, by default, when you start up a GHCi process, it runs the command GHCi, and we want to run cabal-dev GHCi. So if you use Control-U before Control-C, Control-Z, it will ask you for the command to run. And since cabal-dev needs to be inside of the directory that you're working in, we'll use the shell to first change directory to the Pandoc directory, and then run cabal-dev GHCi. Let's load the module we're interested in again. And enable rainbow delimiters. And then test one more time what we did previously, which was read Markdown, default parser state, and then a header. Great. Now, I'd still like to run parsers directly, so let's look at what read Markdown is doing. It looks like it's a wrapper around read with. So read with is a function that takes a parser state, a list, which we can assume is a list of characters or a string, and returns a value. And Parse Markdown is a parser that returns a Pandoc value. Now, Parse Markdown may look like a pretty complicated function at first. It deals with the parser state, it handles references in a first pass, and does some other stuff. But what we're really interested in are these three lines here. The first parses the metadata for the document, if it exists. The second is Parse Blocks. And then finally, it constructs the Pandoc value from the blocks that it parsed. So let's take a look at Parse Blocks. Parse Blocks is another parser that parses many blocks. And then block is another parser which looks like it parses any one of these block parsers. So back to what we were trying to do, let's try read with header, a default parser state, and code deconstructed. And it worked, but there's a parse error. There's an unexpected end of input. And if you remember looking at the read markdown function, it adds some new lines to the end of the string that you give to parse. So let's try that. And there we go. We have a header. So what exactly is a header? Let's look at the type of what we get back from this function. And it's a block. And a block is an algebraic data type defined by Pandoc that corresponds to the block types you defined in a markup document. So there's some plain text, a paragraph, a code block, block quote, bulleted list, and so on. And we saw some of these when we took a look at the native output format earlier. So Pandoc is building a tree of different blocks and other elements inside of that. You can also see that there are some inline elements as well, which we'll look at later. I'd like to see now how the header parser itself is written. And it looks like it's either a set.txt header or an Atx header. This final bit of code here is telling Parsec how to report an error if this parser fails. Now, if you look at the markup specification, the Atx header is a header that's preceded by hashes, and the number of hashes indicates which level of the header it is. There's also a set.txt header, which is an underlined header. So let's look at the Atx header first, since that's the simplest and that's the type of header we've been looking at so far. So first, the parser reads one or more hashes, and that determines the level of the header. Then it looks to see that the hashes aren't followed immediately by a dot or closed parentheses, which is presumably an extension to Markdown by Pandoc. It skips any spaces. Then it parses many inline elements up to optional closing. And then finally, it returns a header. So you can see it's returning header, level, and text, which is a block value. And the header level we saw earlier, it's 1 in this case. If we would have added more hashes, we would have gotten a different level of heading. So set.txt headers are a little bit more complicated because the indication of the header follows the text of the header. Let's skip the first line that says it's for performance reasons. We'll come back to it. And look at the rest of the parser. So similar to the Atx header, it parses one or more inline elements, this time followed by a new line. Then it looks for 0 or more underlined characters and some blank lines. Now that may not seem right at first, 0 or more underlined characters. We really want 1 or more underlined characters, but it works because that's taken care of in the first line, which is a lookahead parser that checks to see first, it ignores the line that it's looking at and looks after that line for 1 or more underlined characters or set.txt header characters. And that guarantees that when we actually, if the lookahead succeeds, that the parser will find underlined characters. So why is this lookahead here? The comment indicates that it improves the performance of the parser significantly. And to understand why, we need to look at the try I've been ignoring up until now. Try tells Parsec to attempt the parser following it, And if it fails at some point, to backtrack to where it was so that a parser doesn't consume some input and then fail, leaving some unparsed string. In this case, I suspect that the performance boost comes from the fact that if we were to parse any number of inline elements before looking for an underlined character, if we encountered a long paragraph, for example, it would succeed with this parser up until it looked for an underlined character, and then it would fail. So you can imagine this parser running on a large document, and the header parser is attempted on every paragraph that it finds until the end when it doesn't find any underlined characters, and the parser has to rewind back to where it was before attempting any other parsers. Let's actually look at the set Txt Header Parser and test it out. But before we do that, I don't want to keep typing default parser state, so I'm going to define an alias, parse, that takes a parser and is just read with the parser default parser state. So now we can rewrite the above as parse header. And now let's test it with a set Txt header. And I'm going to use GHCi's multi-line input so that you can see a little bit better what's going on. So we'll parse a header, code deconstructed, a new line, and we'll break the string onto multiple lines. There we go. So you can see that the header came back, and if you really want to check if the Txt header is what's being applied, we'll do it again with that directly. There you go. Now let's take a look at another parser. Markdown supports what are called block quotes, which are familiar if you've seen them in email before. Here is a quote. And the interesting thing about block quotes is that they support nesting more Markdown inside of them. One use of this is a nested quote. Here we have a block quote within a block quote. And you could also have a Markdown document that's been quoted. So let's take the header we've been working with until now. Now there's block quote, header. How is the parser written so that it can handle this? Let's take a look at it. Block quote. So first, the parser parses an email block quote, which we can see above. Then it runs parse blocks on the result of that parser. And parse blocks, we saw earlier, is used at the top level Markdown parsing. So Pandoc is essentially using recursion here. First, it parses the block quote, then it treats the contents of the block quote as an entirely new Markdown document, parses the blocks out of it, and then returns it in a block quote block. I'm not going to explain email block quote for the sake of time, but I want to point something out that may trip you up if you're not familiar with it. If you look up above at email block quote start, there's an operator that you may not have seen before. And if you try to search for this operator on Google, you'll come back with no results. If you've worked with Haskell source long enough, You'll know that Haskell developers are fond of defining new operators, and I'm guilty of it myself. So let's search the source for this operator. And it's defined in parsing.hs. And it's basically a shortcut. It flips the order of the plain double arrow operator so that this parser email block quote start, instead of returning an optional space, it'll return the greater than symbol that it parses on the left side. Now, we've looked at some block level elements. What about inline elements like emphasis or links? We saw mention of that briefly when we were looking at the header parser, specifically ATX and setATX functions. You can see in Atx Header that many inline elements are parsed that make up the header. And if we look at the inline parser, it's similar to the block parser we saw before. It's essentially a choice from among these inline parsers. So why don't we give one a try, like emphasis. And rather than picking the exact parser we want, we should just be able to use the inline parser and it'll select the correct one. And there you go. And if we check the type of this, it's inline. And looking at what inline is should be familiar by now. Now, there are a lot of other parsers in this file that we don't have the time to look at together. But I'd like to point out a few that looked particularly interesting. The first is null blocks, and if anyone knows the story behind that, please send me an email. I'd be interested to hear it. The second is the parser called force, and finally there's a parser called nested. And before wrapping up this episode, I'd like to have a little fun with what we've learned so far. Remember the email address parser we looked at earlier? Why is that inside of Pandoc? Well, one of Pandoc's extensions to Markdown is a simpler format for entering links and email addresses. So normally in Markdown, to enter an email address and make it clickable, I'd have to enter something like this. But Pandoc allows you to use the more familiar syntax here, and it'll automatically detect if it is a valid email address inside that and convert it to a link for you. So let's parse just a block and see what we get. You can see that it's converted it to a link for us. To see how that works, let's search the Markdown file for email address. And you can see this auto link function that detects if the string begins with an opening brace and ends with a closing brace, and it's a valid URI or email address, it will convert it to a link for you automatically. This is the strict state that we saw earlier. There's a command line option to Pandoc to put it into strict Markdown parsing mode, which doesn't allow Markdown within the description of a link. If it's not in strict mode, it will also make this a monospace font. Let's play with something else along these lines. Let's say I write a lot of Markdown documents, and I want to automatically promote any instance of code deconstructed I find in the text. So I'm going to make a parser called auto-promote that's going to be based on the auto-link parser above. And what it's going to do is look for a string. This is a parser combinator. The string code deconstructed and it will return a link with the text code deconstructed, and instead of repeating it, let's store it here. And we'll link it to my YouTube channel. And now let's save the file, and now I don't want to update the copyright information or the GPL version, thanks Emacs. And reload it in GHCi. And we get a warning that auto-promote was defined but not used. So it's not going to work unless we insert it somewhere into the parsing. So let's look where auto link is used, and we'll add it after that, auto promote. We'll reload the file again. And now we should be able to, let's see, read Markdown, default parser state. We should be able to have a document where any instance of code deconstructed is converted to a link. But it hasn't worked here, and to understand why, let's look at what we get back. Code deconstructed is returned as a string. It's actually returned as two strings because Pandoc normalizes spaces. It collapses white space into a single space. But the clue might lie in the string parser, str. And what's happening is, notice that there's no try here. And here, an alphanumeric character is parsed. So I suspect that as soon as the str parser sees the C in code deconstructed, it assumes it has a match and matches up until another non-alphanumeric character. And our parser will never run. So let's go back to the inline parser, and we'll try moving the auto-promote parser above string, because the inline parser uses the choice parser combinator, which tries each of these parsers in sequence. So one more time, we'll reload. And let's parse this document again. And now it's worked. That's it for this episode. I hope you've enjoyed it and that you have a better understanding for how to construct complex parsers with Parsec in Haskell. We've seen how to use lookahead in parsers. We've seen one way to parse a language with a recursive grammar, and a couple tricks for getting code loaded into GHCi so that you can play with it. Thanks for watching, and I'll see you next time.